LAN switching. One of the biggest network innovations of the 1990s was the development of switching in the local area network. Switches kept the operation of transparent bridging and coupled it with advances in the design of the backplane. The result of that was reduced latency, the division of collision domains, and support for simultaneous connections over the backplane. In this nugget, we're going to start off with looking at the characteristics of switches. Then we're going to illustrate the effects switches have on the different domains, the collision domain and the broadcast domain, followed by a look at the operation of a switch and how it is like transparent bridging. And we're going to end up by looking at the three switching methods and illustrate their effects on the local area network. As we outline the characteristics of a Cisco switch, we're going to start with the physical descriptions. What we're going to have is two types of switches in general. Okay, the first is illustrated by these first two drawings. And what it is this is the front view of the smaller type of switches. They're usually 1U thick for the rack mount, 1U here, and on the front face they will have the ports that are available for connectivity to the different devices in the local area network. These are Ethernet ports, and normally they're 10 or 100 and sometimes combination of 10/100. On the back side of these switches, you're going to see the power connection for plug into the wall to the outlets, and then also sometimes you'll have an AUI connection, which is the attachment unit interface. Basically, you put a transceiver on here for some type of Ethernet connectivity. It can be fiber, it can be 10BASE-T. Then we're going to have the console port on the back end, and then simply a fan here rotating through to provide the air for the unit. Now the other type of switches we have are in the larger families like the 5000 or the 5500, and they're somewhat shaped like the concentrators where you can slide cards in to hook onto the backplane of the switch. And what you'll have at top here is two power supplies. So again, power in through an outlet on the wall jack, a fan for circulation of air through the unit, and then the supervisor module. This is simply the brains of the unit, and there has to be a supervisor module in every 5000 switch or 5500. And on that supervisor module, there'll be many ports. One will be the console port for connectivity and configuration. And then again, we're going to have cards that are available for port interface options. Sometimes it will be like the RJ45 connections you see here for 10BASE-T connections or 100 base. And then other times there will be ATM connections, gigabyte connections, things of that sort. Keep in mind that when we're defining these general physical characteristics of the switches, it's just to give you a comfort level of what we're talking about in a physical sense. So when you walk up to a switch, it won't be hard to identify either the smaller switches, the work group type switches, or the larger switches. But where the importance comes in is the difference in categories. There are two categories of switches, and they have to do with the operating system. The first of the two is the iOS-based switch. And as you can tell, that's the proprietary operating system to Cisco. So an iOS operating system will be running on the first category of switches. And the second is the CLI-based switch, which stands for Command Line Interpreter. Now this is going to be a menu-driven type of operation on the switch. In fact, let me show you an example here as we connect to a CLI switch. What you have is menus to choose from. M gives you the main menu, as you can see. K is command line. I is for IP configuration. As you go in, let's opt for the menu. Let me give you a bigger view here so that we can take it all in. As I chose M, now I have a series of variables that I can choose from for other operations within that menu, and I can always return up to the main menu by simply pressing X, as you see here. And that's how you're going to configure this device, running through each of the menus until you get to the option that you would like. Now again, there are pluses and minuses of each type of configuration. Some people feel more comfortable with the iOS type of interface so that you can know the command, get directly there, and have that desired effect, rather than having to fish through the menus and going down to the desired level and then eventually opting for the correct checkbox or option that you would like. Regardless of whether we're talking about an iOS-based switch or a CLI-based switch, the operation within the backplane of that module is going to be the same. And it, as we stated in the intro, is like a bridge. In other words, it keeps the same learning, forwarding, and filtering capabilities that a bridge does, but it operates differently. There are advances in the backplane. So let's go into that for a second if we can. In a bridge, what we're doing is we're taking care of bridging in software. So a piece of the software makes the filtering, forwarding, and learning decisions, okay? Now when we're talking about a switch, those decisions are made in hardware, specifically in what is called an ASIC. Okay, now that ASIC is going to reside on each interface. Each interface then has its dedicated ASIC, let's say right here, as you bring traffic into the switch and as it exits from the switch. Now, ASIC stands for Application Specific Integrated Circuit. Okay, so it's its own circuit specific to the application of bringing packets into the switch, learning about them, filtering, and forwarding, making those decisions. So you ask at this point, okay, I understand that a bridge works in software and a switch works with hardware, but what does that mean to me? Hardware is much faster, okay? So what we're really talking about is cutting down on the latency, which is the time that a packet resides in your network device before it exits that network device. So what we're doing is we're cutting down latency by taking care of our operations in the hardware versus the software. And what makes that happen is these dedicated ASICs. As we go through our discussion on switch operation, keep in mind that there are different physical designs for switches, okay? The most popular of which is called a matrix switch. Now, depending on the design of the switch, they're going to have different processes that happen in the background. And those different designs are beyond the scope of the CCNA. For our discussions, we're simply going to cover the matrix switch that has a dedicated ASIC per port, as we have discussed so far. So in other words, data as it comes into port number 1 here, we'll run through the ASIC, which is the brains of the operation, and we'll make decisions for filtering and forwarding, and we'll mark down what has been learned by that packet coming into that port. Then again, we have another dedicated ASIC here for the output of that packet out of the switch. Now, in between the two, we have something that happens on the back plane, and that's where we move into this diagram here. This is a grid, and what is being represented on this side here are input ports. Here, the output ports, okay? Now let's say that we have a switch here where information or data is coming into port number 1. Through the ASIC, it has found out that it needs to run out port number 6, okay? So it runs through the backplane. How does it do that? It finds within the grid where port number 1 as an input port, port number 6 as an output meet. And here we go. And in that piece of the backplane will be taken up with traffic, okay? Now keep in mind that if we had information coming in on port 2 that is exiting port 5, we could run that information simultaneously because of the grid design of the backplane, okay? So that's very important. This is what's going to give us simultaneous connections being operated on this backplane. And because we have that, we can populate our switches, as you see here, with multiple ports. Keep in mind that a bridge is a layer 2 device, but normally that bridge, what you're going to see is a box with an input port here and then an output port only that services local area networks on each side, right? Which is a collection of devices within that local area network. Here, because of our advances in the backplane, each of these ports can service one individual device. Let's say N1 here, N2, and so on. This will continue so that every device now has its own collision domain and serves as its own local area network. To avoid any confusion, let me make a clarification on the statement I just made. When I referenced this port as an input and this port as an output on a bridged environment, keep in mind that was just because of the direction of traffic from this local area network to here. On the return path, this would now be the input at this port, and this would be the output. So in other words, I have unidirectional ports on a bridge, right? The point being made there was that I can support multiple unidirectional ports on a switch because of the design of the backplane, far more than we did on the bridge. Even with all these advances in design, you've got to keep in mind that a switch is still a layer 2 device, and because of that, it has the same effect on collision domains and broadcast domains as a bridge did. They're both layer 2 devices, and that is what defines their effect on collision and broadcast domains. So let's have a discussion on that, kind of a review from transparent bridging. As I have devices, N1 let's say, out on this network, N2, N3, didn't look like a 3, there we go, and then 4. In the early days of networking, there would be a shared wire here. This is going to resemble a 10-base-2 network. So one dedicated piece of wire, and off of there, tapped into it, in fact, are the devices, okay? So every time that N1 wants to transmit, it is going to run that transmission across this wire. And because it's doing that, it's taking up the wire, which means that N2, N3, and N4 cannot transmit across that wire because they have a shared environment right here that they need to account for. That shared environment is what we define as a collision domain, because there's a possibility of two devices sending packets out simultaneously and causing a collision somewhere on that network or on that wire. Okay. The next step that came through, we moved from 10 base 2, a little bit of a history lesson, into hubs. Okay. All that simply is done there when I have a hub is I take that wire that used to stretch the length of a hallway or the length of a network and composite that into a boxed environment. So I have one networking device that logically has that same shared space inside the box. So now what I'm going to have is I'll have those same devices out here, N1, N2, N3, and N4, vying for position on that wire. Even though they're connecting into a box now, a piece of hardware, rather than tapping directly into the cable, inside that hardware I still have this same shared bus system is what it's termed as, okay? Because of these characteristics, that's why we define a hub as being part of layer 1 on the OSI model. Then we moved into bridges, which was part of layer 2 of the OSI model, and simply stated a bridge could be interjected in between multiple hubs there and support local area networks. Each of these ports on the bridge, port number 1 and port number 2, separated the collision domain, and that is because out on this local area network, each device that was connected to it, let's say N1 and N2, as they transmitted across the wire, had the possibility of colliding somewhere here on the backplane. And the same thing held true on the other side for N3 and N4. But a transmission from N3 could not collide with N2 because of the bridge. They separated the collision domain. So let's go over this here. 10 base 2 networks in the old days, we had one collision domain throughout the network. With the interjection of a hub, it was a cleaner design, but we still had one collision domain. Then with the bridges, we had, in this case, multiple collision domains. In fact, we had 2. Now, because of the backplane and the speed of it and the allowance for many ports being on a switched environment, we could actually dedicate these ports to individual connections, one for N1, one for N2, one for N3, and one for N4. So the result is the same as a bridge. We're dividing collision domains. It's just the division affects fewer devices, where here we were dividing LANs, so both of these devices were affected by one port division. Now we have dedicated ports running to each of those devices. So this is here one collision domain in and of itself. The same with this connection, and so on. Every device that is connected directly into a switch constitutes one collision domain. So in our environment here, now I have 4. In other words, 1 for each device. Let me give you a repeat analogy, if I can, from transparent bridging to help understand this a little bit better. Let's say I have a couple of lanes here for a track meet, and I have a runner here. Now this runner has hurdles within the lane that he's running, and each of these hurdles represent a network device, okay? So these layer 1 devices can be cleared by this runner. In other words, they're hubs. So this runner represents collision domains, okay? So these collisions can go over hubs. In other words, they're not stopped by hubs. As soon as I interject a hurdle that is a bit taller that cannot be cleared by the collision, now our collision domain is broken. And this taller hurdle is representative of a bridge or a switch, which is a layer 2 device. So you can think of this as layer 1 hurdles and layer 2 hurdles. Now, if I have this same track and these same hurdles, but now I have a different runner, and in fact now a taller runner that I'm going to label a broadcast, then I am going to be able to clear each of these hurdles to include the layer 2 hurdle, because it will not break a broadcast domain. Okay, what's going to be required there is what we're going to refer to as a layer 3 hurdle, and this is going to be commonly known to you as a router, a layer 3 device. So to keep this in short, collision domains. In an old 10 base 2 network, I had 1. In a hubbed environment, I have 1. In a bridged environment, I commonly have 2. In a switched environment, I have whatever number of devices are directly connected into those switch ports. Now for broadcast domains, broadcast can clear layer 1 devices, so I have 1. They can clear layer 1 devices here in the form of a hub, so I still have 1. They also clear layer 2 devices, so in the case of a bridge and a switch, I still have 1 broadcast domain. In other words, this network in its entirety is 1 broadcast domain. If N1 sends out a broadcast, it will be heard by N2, N3, and N4. So far in this nugget, we've defined the physical characteristics as well as the logical characteristics of switches, and we saw that there's two types, the iOS-based and the CLI. Then we looked at the domain effects. That's what we just covered. Now we're going to see the operation of a switch and how it is much like the operation of a bridged environment. Let's start this discussion with an explanation of the environment we're working in. We have here a large representation of a switch, okay? And then we have four devices, N1, N2, N3, and N4, that are connected to different ports, as we see here, of this switch. We have a representation here with the dotted line of the backplane of the switch. In other words, that matrix or grid backplane, okay? And then we also have the MAC addresses here, the media access control addresses, or sometimes referred to as the physical addresses. Remember these from an earlier discussion in an earlier nugget. What we're going to have is 00065B. Now this is going to be common, the vendor, if you will, the ID of each of these MAC addresses. After that, we're going to have a series of 1s for N1, a series of 2s for N2, 3s for N3, and 4s for N4, okay, to keep everything simple. What we're going to have represented over here is the CAM table. If you recall in our discussion over bridges, we had a bridge table. It's simply labeled differently but operates the same. This is a content addressable memory table. It's going to record MAC addresses and what port they exist out of, exactly as a bridge did. This represents the learning portion of the bridge, okay? We had learning, forwarding, and filtering. Based on what has been learned, we will make the decisions to forward or filter, and we're going to represent that down here through actions as we run through different scenarios of each of these devices sending traffic to each other. Let's jump right into it. The first thing we're going to have happen is frame number 1 being sent, and that's going to run from N1 to N2, which in our diagram here is from this device over to this device. What's going to happen in the switch is it's going to look at the source address of the packet and the destination address. The first thing it's going to do with the destination, it being N2, is try to figure out where to send that packet. Okay, so here we have our CAM table. It consults the CAM table to see what's been learned. So far, nothing. So it has no choice but to go with the default action of forwarding out every port except for the port that it came in on. So we're going to forward now out of ports 2, 3, and 4. Now, obviously, that's going to get to N2, and the communication will be successful, but we will also have traffic over here on these ports that did need to go out there. This is a learning device, so right off the bat, it's not going to be running at its optimal configuration, okay? Now, because it is learning, what did we learn here? It learned from the source MAC address. So it learned that, and I'm going to leave off the vendor ID. It learned that 111111 as a MAC address existed out of port number 1. Okay, let's move on to the second frame. We're going to have the answer now from N2 over to N1. Again, the first thing it does, look at the destination MAC address, which is the series of 1s here after the vendor ID, and it says, hey, you know what? I know that exists out of port 1. So now it's going to be a combination of filtering for ports 3 and 4. Now this is different than we did on our bridge because we only had the 2 ports available, and forwarding out of port number 1 so that we can reach N1. In this transfer of data, we also learned something new. We learned that the MAC address of 222222 exists out of port number 2, so we're populating our CAM. The next instance that we're going to have of traffic coming through is frame number 3, and we're going to have N4 trying to communicate to N2. So as you can see here, from here across the switch to here, the first thing we're going to do is look for that destination address within the CAM table. We've got it. So this time it's another combination of filtering off of every port except for the one that it came in on, and now that we know the addressed port, the one that it's supposed to go out on. So in other words, we're going to filter on port number 1 and port number 3, and we're going to forward on port number 2. This will result in the packet obviously getting to port number 2, and we learned something new because N4 was a source. We learned that 44444 exists out of port number 4. All right, now we have an answer. Our fourth frame going out is sourced at N2, destined for N4. Looking at the CAM table again, we see that the switch knows exactly where to send that, and so we're going to filter as an action out of ports 3 and 1, and we're going to forward out of port 4. Now keep in mind, as I'm listing these filter and forward ports, I'm never listing the port that's the source. In other words, for these two here, the forward and the filter combinations, I didn't list port number 2, and that's because as a rule, the layer 2 devices do not forward information out of the port that they received on, because obviously that information already exists out there, right? So just keep in mind, each of these pairs, like this next one, was sourced at N4. Port number 4 wasn't involved in either the filtering or the forwarding because by default it's filtered on. The source of that last exchange was N2. So looking at our CAM, we learned nothing new because we already had that information here for N2. All right, the next frame to be sent out, this time is going to run from N1 to N3. We're going to look for the destination of N3. We don't see it anywhere here on our CAM, right? So this action is going to be to forward, simply out of every port except for the port that it came in on. Okay, did we learn anything new with the source being N1? No, the information is right here. Okay, so let's move on to the next transaction. The next frame to be sent is going to source from N3 and be destined to N1. So as far as N1, we see the MAC address here. It exists out of port 1. So we're going to filter out of ports 2 and 4, and we're going to forward out of port number 1, so that obviously this traffic will get to N1. Did we learn anything new because of the source? Yes, we did. We learned that 3 exists out of port number 3. Here now we have the knowledge of every device on our switch within our CAM table, and that is a good step in the right direction, obviously, because now there will not be instances to where we will forward to all ports except for the one that it came in on, unless it is a broadcast packet. Now, broadcast is represented by all F's in the MAC address. Now, remember that you have 12 characters available on your MAC address, right? So each of those being an F represented in hexadecimal means a broadcast packet. So the next thing we're going to illustrate here in number 7 is having N1 send out a broadcast packet. So obviously that's going to represent all the F's. The action that's going to happen in that case is a forward out of port 2, 3, and 4. And the reason for that is you will never see the broadcast address learned here in the CAM because you only learn based on source address, and you'll never source from a broadcast address. So this will always result in forward out of every port except for the port that it came in on. In the last section of this nugget, we're going to talk about switching methods. We're going to talk about 3 switching methods. But first, let me define what a switching method is. Simply put, it's how much of the packet or frame, whichever you're familiar with or comfortable with, needs to be received before transmitting to the destined end. In other words, coming in on one port into the switch, how much of the frame has to be received before we start outputting or transmitting that information to the destination or destinations, whatever the case may be. So to start that discussion, let's take a look at what the frame looks like. We have a destination MAC address first, and it has 6 bytes represented with that destination address. Then we have the source address. These are physical addresses, remember, or MAC addresses. Then we have a field here, this is the type field, 2 bytes long. Then we have data. This can vary from 46 bytes to 1500 bytes. This is all the encapsulated information from the layers above layer 2. And we end up with the CRC, the cyclic redundancy check. Basically what it's going to do is just make sure that the data integrity is held within these portions of the packet. Okay, so it's a checksum at the end of the packet. Now with store and forward, what we're going to do is we have to receive all of that frame or packet before we can transmit out. Let me give you a bit of an analogy. Let's say that this was the airport baggage claim. I know these kind of don't look like it, but let me explain it. Maybe it'll look more like the baggage claim environment. Simply put, the bags come up here, they drop down, and then they circle around, and there's hordes of people standing around here trying to claim their baggage. These turning doors represent the entrance into the baggage claim area from the rest of the airport, and then the exit. Once baggage is claimed, you proceed to the exits. Okay, with store and forward, what we're saying is that there are people here customs agents, if you will, that as you try to exit, they're going to verify information. They're going to verify, in the case of this analogy, that the tags are right. They match the bags. They're also going to go through your bags in some instances and verify that you are not smuggling something into a country that is not supposed to come into the country from another, okay? So this represents store and forward. It's not only a verification of specific smaller pieces of information, but also a look at the baggage in its entirety, which is what we're going to do here. We're going to receive into memory this whole unit, and then once we have it in its entirety, then we will start transmitting out. Now, while this helps us because there are less errors, as in the case up here, there is less of a chance of something coming into the country that should not be. At the same time, it induces latency, so it's slower than the other switching methods, but in some cases you may need that because you have an unreliable network. In the case where you feel that your network is reliable and you want less latency on your delivery of packets or frames, then you're going to opt for what's known as the fragment-free switching method. Again, looking at our unit here, what we're going to have within the frame is the destination address, the source address, and the type. Together, these are 14 bytes. Now, fragment-free is going to accept 64 bytes of data prior to transmitting information out. Here's the variable. Within the data, we can have as few as 46 bytes or as many as 1,500. Let's say, for example, that we had the 46, okay? We have 14 here with the 46. Together is 60 bytes so far. Introduce the CRC, that's 64 bytes. So in many cases, for smaller frames, in fact, the smallest you can get, this is the frame in its entirety. So it might not be that much different than store and forward. So as you're making these switching method decisions, you need to have some familiarity with what's running on your network, because if you have a bunch of small packets like this, you're not gaining much by going to fragment free, because store and forward is the same operation for small packets. Okay, let's say that they're larger, then you are saving time in that respect. Let's say that 1,500 is what you have here in your data size. Then definitely a portion of the packet is coming into the switch, being accepted into memory, and then decisions are being made for the transmit. So let me give you an analogy. Again, with our airport analogy, we have the input into the baggage claim area. In that baggage claim area, if we are flying from a United States source to a United States destination, we would normally have just an individual here verifying that your tag that you have in your possession matches the tag that is on your luggage as you exit. It's not as extensive as customs. In other words, just a piece of information is verified. Representative in our frame here by 64 bytes, okay? And then the decision made is to transmit out. This is going to result in less latency, which is a big improvement over store and forward, but you've got to make sure that your network is reliable enough so you don't run into the errors that can be caused. The good thing is, by 64 bytes, most collisions take place prior to 64 bytes being transferred. And also, a runt is defined as a packet that is less than 64 bytes. So right here, you're taking care of 90% of the problems you may have in a frame just by accepting up to 64 bytes. Now, for those administrators that are more daring and speed is a priority, we offer the cut-through method. Simply put here, all you're going to wait for is this destination address. It's all that you really need to send the packet out, right? So in other words, packet will come into this port, you see the destination address, you're not even really going to store much in memory at all, and automatically you're transferring out. Now, you are open to collisions, as we had said before, runts, things of that sort, but if you have a reliable network, this can save you a lot of time. Again, to our analogy, let's say that you're going into the baggage claim area. Once you have your baggage, and this happens in many airports, in fact, more than I'm comfortable with, you're able to exit that airport without your ticket matching your bag. Now, I guess what you're really on here is the honor system, right? And that's what cut-through pretty much represents on the network. You're on the honor system of your network being so dependable that you can simply know the destination address or destinations and simply transmit that packet out those ports or that individual port. These switching methods are available for an administrator to set within the switch on a per port basis, but you got to keep something in mind. Let's say that I have a switch here, okay? I have an input port here in port number 1, and in this case, the output port on this side, let's say, is 12. I have a speed coming into this input port of 100 megabits. In other words, I'm talking about fast Ethernet coming into this port. Leaving this port, I have 10 megabits. In other words, just 10 base T. All right, because of the difference in speeds here, No matter what you have set on those ports, the switch is going to make a decision for you, and it's going to opt for the store and forward. And the reason it's going to do that is because it needs the entire packet before it's able to forward out this differing speed port. So just keep that in mind. Regardless of what you have set on that port, this is going to be the default option for ports that have different speeds set. We started this nugget by looking at the different physical characteristics that you might find in switches. We also saw that there are two categories of switches, the iOS-based and the CLI-based, which was the command line interpreter, pretty much menu-driven configuration. We also saw the effects on domains. Collision domains are divided by switches. Broadcast domains cannot be. In the operation, we saw that it operates much like a transparent bridge, except for the fact that we now have individual devices on those ports because of the advances made on the backplane, rather than having two LANs divided, as we did with a bridge. And we ended up with our discussion on switching methods. We saw that store and forward accepts the packet in its entirety prior to transmitting out the destination port. And then we saw that fragment free accepts 64 bytes of the packet and then makes its decision. This helps guard against collisions and runs. And in the end, we saw for administrators that are focused on speed, the cut-through switching method that simply looked at the destination address and forwarded that packet out and relied on the network for protection against collisions. I hope this has been informative for you, and I'd like to thank you for viewing.